Why does the Earth orbit around the Sun? Since the dawn of time, humans have pondered the question, why does the Earth revolve around the Sun? The answer lies in the powerful force of gravity, which binds the Sun and the planets together in our solar system. The Earth is held in orbit by the Sun's gravity. The Sun's gravitational force is strongest at its center. Therefore, planets that are closest to the Sun will be pulled in tighter. This is why the Earth's orbit is elliptical, meaning it is closer to the Sun at certain points and farther away at others. As far as we know, this dance will last up until the Sun dies. Nowadays, it's not hard for us to believe in such things. Everything seems quite normal and trivial to us. But if we go back, we soon realize how difficult it for humankind was to reach this self-consciousness level. Back then, scientific concepts weren't as trivial as you think. Keep watching the video to get to know more about the forces that keep the Earth, the Moon, and other planets around the Sun. Spoiler alert, the same laws apply to exoplanets and exomoons. Historical context. The concept of heliocentrism, that is, the idea that the Earth revolves around the Sun and not the other way around, has been around since the time of the ancient Greeks. The ancient Greeks believed in a geocentric universe, where the Earth was at the center of the universe and was the stationary point around which all the planets and stars revolved. It was not until the time of Nicholas Copernicus, however, that heliocentrism began to gain traction. Copernicus was an astronomer and mathematician who published a book in 1543 called On the Revolutions of the Celestial Spheres, outlining his heliocentric model of the universe. His model attempted to explain the observed motion of the planets by postulating that the planets rotate around the Sun and do not revolve around the Earth. In addition to Copernicus, two other influential figures in the development of heliocentrism were Galileo Galilei and Johannes Kepler. Galileo studied Copernicus's model and was one of the first to observe that Venus went through phases like the Moon, which confirmed the heliocentric model. He also observed the moons of Jupiter and used the idea of heliocentrism to explain them. Kepler was a mathematician and astronomer who discovered the three laws of planetary motion, which described the motion of planets around the Sun in mathematically precise terms. The concept of heliocentrism was met with much resistance from the Church, which held to the geocentric view of the universe. This eventually led to Galileo's trial for heresy and ultimately to the acceptance of the heliocentric view of the universe. Today, heliocentrism is accepted as a scientific fact, and we have sophisticated tools like telescopes and satellites to observe planets and stars more accurately, allowing us to further understand the heliocentric model and its implications. Observational evidence. The evidence for heliocentrism became stronger when Johannes Kepler, a German astronomer, noticed that the orbits of planets around the Sun were elliptical. His contribution to the scientific world has been immense. He was the first to propose that galaxies were composed of stars, and that stars moved in patterns. His work on the nature of light and the laws of geometry are still used today. He also developed the first modern telescope. But what really throws some astronomers for a loop is Kepler's three laws of planetary motion. The first law: every planet orbits the Sun in an ellipse, with the Sun at one of two foci. This one is so predictable that it's almost boring. The second law: a line between the Sun and a planet sweeps out equal areas at equal times. This one is a little more interesting. The faster a planet is moving, the further away from the Sun it gets. That's why the solar system's outer planets take longer to orbit than its inner planets. The third law: the square of a planet's orbital period is proportional to the cube of its average distance from the Sun. This one is the most interesting because it allows astronomers to predict the orbits of planets, moons, and asteroids. But here's the thing. Kepler's third law is sometimes referred to as Kepler's fun law. This is because astronomers often play a game called Kepler's fun. The object of the game is to use the equation to calculate how long it would take a planet to orbit the Sun if it were twice as far away. It's a great way to pass the time and a useful tool for teaching kids about the universe. For those looking for more than just a game, Kepler's laws can provide useful insights into the nature of the universe and how it works. But for now, let's just enjoy the game of Kepler's fun. It's a great way to explore the solar system and have fun doing it. Perhaps the observational evidence that contributed the most to the fall of geocentrism came from Galileo Galilei. The famous scientist and professor conducted several experiments in 1609 and 1610 to observe the moons of Jupiter and prove that the Earth was not the only body revolving around a bigger object. His observation demonstrated that the planets revolve around the Sun, and from this evidence, he concluded that the Sun, not the Earth, was the center of the solar system. This observation by Galileo helped to solidify the heliocentric model of the solar system. It also demonstrated that the universe was more complex and that our understanding of it needed to be updated to include heliocentrism. So we know that the planet Earth revolves around the Sun, as well as all the other planets in the solar system. But will it ever stop doing so? Stability of the orbits. The revolving of the Earth and other planets around the Sun keeps the solar system in a stable state. Without the Earth's orbit, life as we know it would not exist. It is the gravitational pull of the Sun that helps keep the planets in their orbits, providing us with the warmth and light necessary for life. As long as the Sun remains active, it is highly unlikely that the Earth and other planets will ever stop orbiting around it. The Sun has been around for 4.5 billion years and is expected to remain in its current state for at least another 5 billion years, so the planets will continue to rotate around the Sun for a very long time. The orbits of the planets do not remain the same over time, however. Although the orbits remain stable, they can drift slowly over time due to gravitational influences from other objects in the solar system. The most notable example is the eccentricity of Mercury's orbit, which slowly increases over centuries due to the gravitational pull of other planets. There are also external forces that can alter the orbits of the planets. In some cases, asteroids or comets can pass close enough to the planet to alter its orbit. Even the slightest change to an orbit can have drastic consequences, such as a planet drifting away from the Sun or crashing into another planet. In conclusion, although the orbit of a planet can change over time, it will remain in a stable state as long as the Sun remains active. Exoplanets and exomoons. But what about exoplanetary systems and exomoons? Even though they are much further away from us, they still follow the same laws of physics and orbital dynamics. This means that many of the principles that we understand to be true for our solar system also apply to exoplanetary systems. In particular, exoplanetary systems exhibit the same stability as the solar system. Like the Earth, exoplanets are held in orbit by the gravity of their sun. This powerful force binds the exoplanetary system together and keeps the planets in a stable state, preventing them from drifting away or crashing into each other. The same laws of physics that govern the behavior of the planets in our solar system help to keep the exoplanets in orbit, providing the same level of stability for those distant universes. The eccentricity of exoplanetary orbits may also be affected by interactions with other objects in the system. This can cause the orbits of exoplanets to drift over time, like the orbit of Mercury in our solar system. The external forces of passing asteroids or comets can also potentially alter the orbits of exoplanets, although this is much less likely as they are much further away from the Sun. We don't really know much about exomoons because we never really observed one. Nevertheless, we are sure they exist. I mean, they must exist. It would be really weird if they didn't. Finding an exomoon is another level of difficulty. They are even smaller and harder to detect than exoplanets. It would be similar to trying to detect a tiny grain of sand near a headlight miles away. Nevertheless, Columbia University astronomers may have detected the first ever exomoon. Alex Tichy and David Kipping combed through Kepler data for hundreds of exoplanet detections, and one record stuck out. The data indicated that the star Kepler 1625, 8,000 light-years away, had dimmed once from Kepler 1625b, a Jupiter-sized planet passing by, suggesting the presence of an exoplanet. But curiously, it had also dimmed again within a day for a similar amount of time. It couldn't be the same planet. There wouldn't have been enough time for the planet to loop around in a matter of hours, because a single orbit should be around 287 days. And it probably wasn't a second planet because another planet traveling at the same speed as Kepler 1625b would share its orbit and likely collide with it, while a planet in a different orbit would travel faster or slower than Kepler 1625b. Then finally, could this be an object trailing just behind the planet? Maybe this was an exomoon. This video published by ESA shows what they actually saw. This might be the first convincing evidence for an exomoon. In conclusion, the stability of exoplanetary systems is largely reliant on the same forces that keep our solar system in equilibrium. This is the strength of physics. Provided the conditions are the same, the laws stay the same everywhere in the universe. The power of the star's gravity controls the orbit of the exoplanets, providing stability to their systems. Although the orbits may drift over time, the same laws of physics apply, ensuring that the exoplanets remain in a stable state for a very long time. It is an incredible thought to realize that the Earth's orbit and the Sun's gravity combine to keep us safe and secure in our own solar system. So the next time you look up in the sky, remember that it is the Sun's force of gravity that is keeping the Earth in its orbit, allowing us to exist and thrive.